Hello, everybody, and welcome to the third video on this second ice day. If you saw the first video, you'll recognize this reaction called reductive amination, in which we can create complicated amine molecules after creating first an imine that is then reduced. If you remember the second video from today, we talked about the process of keto-enol tautomerization, an equilibrium between the keto and enol forms. The last point I made was that the keto form, having a carbonyl, that carbon atom is electrophilic and will react with nucleophiles. We've seen many examples of that already this semester. But then when we have the enol form, even though it's never favored at equilibrium, it does exist in an equilibrium process, but it has an entirely different personality. Instead of being an electrophile, by virtue of the pi bond, that electron density can act as a source in a bond-making process. In other words, it can be a nucleophile, a weak nucleophile. Well, I'm going to double down on that and talk about it in the context of a reaction that's really pretty interesting. It's referred to as the alpha-halogenation of aldehydes or ketones. And it's an interesting process because we take a catalytic amount of acetic acid in the presence of Br2, and we can make a new bond to bromine. But we do that at a specific site, the so-called alpha carbon. And an alpha carbon is the carbon that's immediately adjacent or bonded to the carbonyl. So this reaction works with aldehydes or ketones. We're going to illustrate it using a reaction with a ketone, acetone. So like I said, this process occurs in the presence of catalytic acetic acid. So since we're an acid and we have a carbonyl species, the first thing we're going to do is add a proton. I want to remind you that protons move faster than other species in a given solution. So when in doubt, if you can't think of anything else to do, try to transfer a proton. Well, like I said, we're an acid, so we know that the carbonyl oxygen is going to receive that proton to generate this positively charged intermediate. You're going to recognize this as actually the enol formation mechanism. As a result, the next step, just like last time, is going to be taking this proton from a carbon to create the enol. And now you know why I was telling you about the personality of an enol. Because even though it's not favored at equilibrium, there will be a small amount because of the catalysis, the acid catalysis by the acetic acid. And recalling that the enol has the personality of a weak nucleophile by virtue of the pi electron density that's associated with the double bond. So it can react as a nucleophile as long as it reacts with a strong electrophile. And Br2 absolutely counts as a strong electrophile. The reason being, if you react with one bromine atom of Br2, you break that bromine-bromine bond, which is a weak bond anyway, and you generate a very stable bromide anion. So this is a really good electrophile. And it turns out that the lone pair on that oxygen actually assists in this process. And we're going to make a bond here to the bromine to generate that positively charged intermediate and the bromide anion. When we look at this, we say, okay, what we've got to do now is somehow get rid of that proton, because then we'll have a stable species, which we know is the product. And probably what is a surprise, I'm not putting Br minus here, because it turns out if you take a look at acetic acid, even the protonated form of acetic acid, compared to Br minus, the standard acetic acid in its protonated form is actually a stronger base, believe it or not, than the Br minus. I would not have expected you to know that. So we're going to take a proton away in this last step, and that's going to generate our final product in this protonated acetic acid, which is a very strange looking thing, but that's what you end up with at the end of this process. I just want to emphasize that that carbon is in fact the alpha carbon, and that's where the bromine goes. So when we look at the KRE here, it's a new bond to the alpha carbon with the bromine atom. Okay. Why is this interesting? Well, it turns out this reaction is very interesting from a synthetic point of view. Let me give you an example. Let's start with acetone again. And I'm going to react that under these conditions to generate the alpha bromo product. Okay, fair enough. What I'm going to do now is I'm going to convert this to a Wittig reagent. It's a halogenated product, so I can react it with triphenylphosphine, followed by N-butyllithium. And what I'll end up with is the following Wittig reagent. Now I'm going to go ahead and add this hydrogen because we're going to want to keep track of it. But we have that Wittig reagent, and I'm going to react this with a carbonyl species. In this case, I'm going to pick one that has a 6-membered aromatic ring and is an aldehyde. And we're going to do a Wittig reaction. And I want you to watch what we're going to get out of this. Remember what we said. When there is a carbonyl group adjacent to, now you know, alpha, to the Wittig anion carbon, you get the E product only. I'll go ahead and make this a little bit cleaner. Get rid of that C. Give me a chance here. This will look a lot better in a second. Here we go. That gives me the E product. And you can see we've made a very complicated molecule from pretty simple starting materials. But the most important point is this is how you access those Wittig reagents that are going to give you that E product. So if you see one of these products in a synthesis problem, so it's a new carbon-carbon double bond with an E geometry and a carbonyl adjacent, you might want to think about using this alpha-halogenation reaction because that's the best way I know of to make those. Okay, I hope this was helpful.